So we shall discuss about numerical differentiation and then solving differential equation, numerical integration. Two techniques we have discussed yesterday: Simpson's method, and even before that, the trapezoidal rule. Okay, so what we shall now look at is solving differential equation. But before that, how to find out differences, because we'll need multiple techniques later. Okay, today and tomorrow we'll discuss both these techniques, and that time we'll need some of these things. Okay, so let me present the screen. Is the screen visible?
Yes, sir.
Yeah. So thank you. So first thing that we are going to discuss is numerical differentiation.
My screen is still not loaded. I'm seeing you only.
Okay.
No, sir, it is visible. Maybe
No, it's
there's
visible.
maybe some problem in the internet.
Okay, then it's only my problem. Don't worry.
Okay. So yeah, so suppose you have got a function, and that function you want to find out derivative at a particular point. Okay, so what can be done is, well, I mean, for visual understanding you may plot the entire function, but if I'm interested in finding out derivative at one particular point, I may take a small range, and I know that within that range the function is not going to be a straight line. But if you go for smaller and smaller range, then we know that any nicely behaving function can be approximated to a straight line. Now here again, multiple times when you come under you encounter this term called nicely behaving function. So what does nicely behaving function mean? Nicely behaving function means the function whose which is differentiable in the given range. Okay, it's continuous, differentiable in the given range, and doesn't go to infinities. Even if it goes to infinity, it may go to infinity at finite points, not large number of infinite points. And the you can differentiate the function at the second order, third order. Okay, and the values are not going towards blowing up. Okay, so then such kind of functions we say are nicely behaving functions. And then for such, you take, suppose I'm interested in taking derivative at one particular point, you take a small range around that, smaller the better. Okay, because you can approximate it to the straight line, and then you straight away use formula y2 minus y1 upon x2 minus x1, which is nothing but delta y by delta x, and you know the derivative. And if you keep on doing this for every point, okay, when I say every point, I mean every whatever interval you have taken. Okay, and then you may be able to plot that entire thing, and you can in fact also plot what could be the derivative function for the given function. Okay, so this can be done. For more precise answers to certain with certain techniques and numerical integration, you may need at times the higher differences, or also to find out the integration. Sometimes you may need to find out the higher order differences. It means when you find out, say, when you are writing y as a function of x, okay, and you find out the difference delta y by delta y, okay, that is the first difference. Now when you find out the difference at the regular interval of those delta y's, then it is delta 2y, and that is the second difference. Similarly, you can find out the differences between delta 2y, okay, at that regular interval, and you can call it third difference, or delta 3y. So these things become useful, but we'll talk about them a bit later. Okay, whenever we need these things. Now what we shall do is, let us take a quick example of how we can do numerical differentiation for a particular problem. Okay, so I'll stop at this moment this presentation, and let me switch on to Excel. So I present the Excel key. And what we are going to do now is, let me take some function and I want to find out the derivative of that. Okay. Now, suppose x is here, f of x or y is here. Okay, let me write y. And x minimum I'm going to write here, x maximum range I'm going to write here, dx I'm going to write here. Okay, and this I know I'm going to say x max minus x min, and say I want to divide everything into interval of 1000. Okay, I'm just taking some number, and this value is going to be whatever is in the lower limit. Okay, and I am going to write formula. You know, this is the standard stuff that we have been doing. Dollar A5 plus $2. That will give me, sorry, that will give me, and I have to put this to next 1000 cells. So effectively, I made my template here. Okay, and I want to write now lower limit, upper limit. I want to decide a function. Let us suppose I'm going to decide, I'm going to take a function, say sine of x. Okay. Now, so I will have to write sine of e phi, and let me copy paste that everywhere. Okay, so yes, my template is ready. Let me write the limits. Suppose I want to do this for, say, 6 pi, 0 to 6 pi. Okay, I'm going to calculate this. Let me plot it also. Plotting, in this case, plotting we are only doing for understanding that, okay, what I'm doing. In numerical techniques, it is not necessary always that you plot, but when you are learning and you know learning techniques, you know some already known function, how things look like. Okay, plotting becomes a useful exercise. Here I'm going to find out the derivative. And how do I find out the derivative? Okay, suppose I'm interested in finding out dy by dx here. Okay, so see, I cannot find out derivative at the extreme points. Why? Because you know derivative, when you want to find out, okay, in the what is the definition? It is say limit h tending to 0, f of x plus h minus f of x upon h. Okay, so finding out derivative at end points is not, I mean, you can't find out because you are assuming that you are extrapolating beyond the range. So it will always start with, say, y1 value. And here what I can write is, this is going to be the next y value minus the previous y value divided by next x value minus previous x value. This is like y2 minus y1 upon x2 minus x1. The brackets neatly, and you can put this up to not up to last point, but second last point. So P1004, and I paste it. Now I need to plot even this function. So when I want to plot this function, see, I will select data and I will add the series. Okay, and my x variables is going to be from this point to second last point. Y variable is going to be this point to, again, yeah, second last point. And I plot this. And what you get, this is a cosine curve that you get. The second curve that you have got is a cosine curve because derivative of sine is a cosine. And here that shift of origin doesn't take place simply because there is no constant of integration that we are talking about. Okay, so you can clearly see that sine x function becomes, when you take the derivative, it becomes cosine x. Now in place of sine x, suppose I had sine 2x. If it is sine 2x, you see I'm changing the function in column B, sine 2x, applying it everywhere. And now what happens? Look at the derivative. It has become double size because it is twice cos 2x. Okay, so the frequency has remained same. Sine has become cosine because it starts at the peak value. And the amplitude has become between plus minus 2. So you know sine of 2x derivative is twice cos of 2x. Okay. Similarly, you can play with this. Suppose instead of sine x, if I take sine square x, what will be the derivative of sine square x? Quick guess. What is the derivative of sine square x? Which is basically sine x square.
2 sin x cos.
Yes.
Sine 2x.
Sine 2x.
2 sine x cos x, right?
Yes, 2
It's
sin
It is
x.
sine
not
2x.
sine of x square. I'm not talking about sine of x square. I'm talking about sine square of x, which means sine x whole square.
2 sin x cos x.
2 sine x cos x. Okay. So when you say 2 sine x cos x, let us see how the function is going to be. So let me apply this formula everywhere. And what you get? You get, see this series 2, okay, is going from +1 to -1. Now, here you see sine square x is all going to be positive. So you see the original function is varying between 0 and 1. Okay. And now this has become 2 sine x cos x. So you see the function is varying between 0 plus minus 1. And there is a phase shift. Okay. When you calculate 2 sine x cos x, derivative of sine square x. Any comment here? Let me check.
Actually, sir, it is also
Okay,
called as
how
sin
to
2x.
apply formula everywhere? That was a question. Now let me quickly check.
Mahesh,
Yes, yes,
2 sin x cos x is also sine 2x.
right.
Right.
Cos
So it
2x.
should have
No,
frequency.
sine. Yeah.
It should show frequency which is doubled. That's not apparent from this graph. So
That is
probably
because, okay, no,
no,
that
your
is because,
syntax,
listen.
put sine fi in bracket.
Wait. That is also correct because sine square x also doubles the frequency. Sine square x is also same as 1 minus cos 2x. Okay. So what has happened here is 1 minus cos 2x upon 2. Okay, so what has happened here is
That's fine, Mahesh.
if you
You're
look at,
right.
yeah, if you look at the blue curve, okay, now let us explain it for everyone. Okay, so what was the argument? The argument was this, that function is sine square x. I will answer that question somebody has asked in the chat, but let us look at this part first, that function is sine square x. So what is happening is, first of all, you see I have given the limit up to 6 pi, which is 3 oscillations. Okay, and you count, there are 1, 2, 3, 4, 5, 6 oscillations taking place. So frequency is doubling. Where is it doubling? So when I write sine square x, okay, sine square x can also be written as 1 minus cos 2x upon 2, which means the frequency is doubled because it is cos 2x. It is 1 minus cos 2x. So see what is happening, and whole divided by 2. So there is half minus half of cos 2x. So what you observe is this entire oscillation has become half because it is oscillating, instead of between -1 to +1, it is oscillating between 0 to 1. And there is a shift of origin of by half. So you see for the blue curve, the center is at half. Okay. Secondly, you see that it is starting at the negative peak. What does it mean? It means it is negative cosine function. Okay. So shift of origin of half with negative cosine function, that is giving you this particular oscillation, and there are 6 oscillation indicating that frequency is doubled. When you take derivative of sine square x, what you get is 2 sine x cos x, which is sine of 2x, as correctly pointed out by Atul sir. So, and what you observe, now this is sine of 2x. So it is a sinusoidal curve, and you observe that sinusoidal curve, 6 oscillations, okay, because it is sine of 2x, and it is oscillating between +1 to -1 because it's just a sinusoidal curve. Okay, so
Yeah,
the
Mahesh,
technique.
one
Yes.
minute. Huh?
Yeah.
I just got little confused with the syntax, because when you put a sign of a5 and then you squared it, right? So instead of taking a5 square, it's taking sine
No,
square
I'm
of
not, because
a5.
I'm not calculating sine x square. I'm calculating sine square of x.
Correct. But
Yeah.
the way you have put it,
Okay.
uh,
So what
okay,
happens is sine function comes as sine with this bracket, and I'm squaring that. So I could have written this extra bracket here, and that is not going to change the value. Now I want to apply this formula everywhere, and that is a question asked in the chat. So how do I apply this formula? What I do is I copy this formula with a keyboard. So you see that this dotted line is appearing now. So the formula is copied, and then I select up to the last cell. And yesterday I mentioned the shortcut for that. So what I do is, if I want to jump to the last cell, I press Control down arrow. But if I want to also select, so I press Shift Control and then down arrow, and I have selected up to the last cell. I have not yet copied. To copy, I will press Control V. So I copy this. You see there is no change in the formula, because sine a5 square is taken as basically sine square of sine number. Okay. If I want sine of x square, let us do that also. Then I will write square inside the bracket, inside that sine function, and this is going to be sine of x square. Okay, and I apply that formula. Again, I have copied that formula, selected all the cells, Control Shift down arrow, and I paste it. Okay, and this is what I'm going to get now here. Because what is sine of x square? See what is happening?
Cos of x square into 2x.
Yeah, cos of x square into
2x.
2x. So there are two things that you observe. Cos of x square when you are doing, and as x is increasing, okay, what is happening is, as x starts increasing, the frequency has to increase, and that is what you observe. In the beginning the frequency is less, and then it starts becoming faster and faster and faster. Also you are multiplying. If you look at this blue curve, original blue curve, it is almost of the same amplitude, because it is ultimately a sine of x square, which means ultimately it is a sine function, has to oscillate between plus minus 1. But moment you are taking derivative, it is 2x times this. So x times cos. So what will happen when you're talking about x times cos of x square? As x is increasing, the amplitude also goes on increasing, and that is what you observe over here. Okay, the red curve, that amplitude goes on increasing because it is x multiplied with sinusoidal function. So of course, if I reduce the limit here, instead of 6 pi, if I put only 2 pi say, okay, then I will get, I mean, you will be able to nicely observe that, okay, that the amplitude is also increasing and it is linearly increasing. So that's the difference, and good, that is important thing that we need to look at when we are writing function. That sine of x square would mean that I will write square inside the sine function bracket, and moment I complete the bracket of sine, okay, the value is ready, so I can directly take square of that. Okay, and let me apply it everywhere, and we get this. Okay, another function that one can look at, I mean, there are multiple things that you can try. Say for example, I want to go back to the function of say e raised to x, and suppose I want to go from 0 to 5, e raised to minus x function. So I will say exp minus a5. I'm taking e raised to minus x, those kind of functions, because many times these kind of functions are going to be useful. They are seen multiple times. And yes, you observe the derivative. You look at this function. The blue function is e raised to minus x. And what is derivative of e raised to minus x? Minus e raised to minus x. So you see the mirror image. Okay, minus e raised to minus x. So this, remember, this particular graphical way is only to check that, Okay, whether my technique is right or wrong. Many times you may not need all this. Many times you may not need to actually plot the graph of all this. This was only to show that yes, things are working nicely, things are working fine. Okay. We can take other kind of functions as well. Say for example, x e raised to minus x and so on. So let us quickly do that. So say a phi into e raised to minus a phi, that is x e raised to minus x kind of a function, and I apply. So I control shift down arrow, I select all things and I apply, and you see what you get. So the function is x e raised to minus x, and the function has a peak at x equal to 1 and then goes down. And when you take a derivative over here, you see the derivative of x e raised to minus x, you can calculate, and that turns out to be this red function. There are certain things that you observe over here. See, this original function has a peak at 1, and you observe that the derivative is going to be 0 at the peak. You expect that, okay? And that is what is happening. So many times you may be interested in finding out, okay, that potential function is given and you want to find out where the force is 0, what are the equilibrium points. Okay, so you know that potential function, if it is having a peak or if it is having extrema, okay, so and force field can be given as negative gradient of potential. Okay, so if the potential function has maxima, then what will happen? The maxima of the potential function would mean that just a minute. Maximum of the potential function would mean that derivative is going to be 0 over there, but that is unstable equilibrium because potential is maximum over there. The minimum of the potential will indicate that that is again an equilibrium point because the force is going to be 0 at that point, where force is gradient, negative gradient of potential. But you displace the object slightly, it will try to come back, and in that case we say it is going to be the stable equilibrium, which means the body will oscillate about that particular point because the force field is negative. And if you expand Taylor, do the expansion in Taylor series, then the first approximation is it is like a Hooke's law force, because any uh, um, curve with a minimum, okay, can be approximated to a parabola. So it is going to be parabolic potential, and parabolic potential is going to be giving you the Hooke's law kind of force, restoring force. Okay, so the body is going to oscillate about that. So we'll have some of the problems in assignment about those, but what I can do is I can take a very quick problem here. Okay, that how does one solve that? During that, if
So,
anybody has a question, yeah, you can ask.
so I want to ask, like, you have written B7 minus B5.
Yes.
So, what will happen if I write B6 minus B5?
Okay.
Can you just?
Then yes, I can write B6 minus B5 upon A6 minus A5. What I'm going to do is I will calculate the derivative between the 2 points in the interval. Okay, because it is shifted in backward direction. So yes, forward differences and backward difference kind of calculations can be done, but I mean, if I want to calculate what is the derivative at this particular point, at say x1 value, then what I should do is I have to calculate the slope at x1. And how do I calculate slope at that particular point? So I take a next point, I take a previous point, and divide by 2. That will give me the slope exactly at this point.
Okay, so we have calculated the slope at a particular x.
Correct. So derivative is nothing but slope of function.
Yes. Thank you, sir.
Yeah. Okay. So let me just take one particular problem where okay, we are interested in finding out the potential function and the minimum of the potential function. Okay. So let us suppose a potential is given by, let me write that here. Sorry. Let me expand this equation. I just copy pasted this particular equation. So if potential is given by, say, V of x is equal to minus V0 some a square into a square plus x square upon 8 a raised to 4 plus x raised to 4, this kind of a function. I am interested in finding out how does this function look like. That is number one. Okay, I also want to find out how the force looks like, and I want to determine the equilibrium points. Okay, and from that I can also determine what could be the frequency of the oscillation if I know the mass of particle, things like that. So first thing is, let us quickly do calculation, or let me because the template is already ready, let me just go back to this particular equation. Let me delete this graph and let me put that formula here. So it is easy for me to write this formula. I need to know what are the values of A. Okay, I need to know what are the values of A. So you are given, okay, let us take A as 2 and A as 5. Okay, so first let me take A as 2. Okay, now I need to write the formula first. So what I'm going to write, remember that X is my A column value and rest all, and V0 also I need to take. So let me write V0 here. And for the time being, I'm taking V0 as 1 because it is just a scaling factor. Okay, it is a multiplicative factor. Whereas A is not just a multiplicative factor because it is coming inside this bracket along with the addition of x square, and also in the denominator where you are adding with x raised to 4 this 8a raised to 4. So A is not a scaling factor, but V0 is a scaling factor. Okay, so let me write this function here. Minus wherever V0 is, I will write that, say $E$2. Actually, it was not required, but for the sake of completion, I'm writing that. And $D$2 square. Okay, you can look at this formula bar, what I'm typing, multiplied by $D$2 square. Okay, plus I want x, which is A5 square, divided by, now there is addition in the denominator, so I will put bracket here. Okay, 8 times $D$2, which is A raised to 4, plus A5, which is my x value, raised to 4. The bracket complete. Bracket for the denominator is complete. Okay, I'm going to copy paste the formula everywhere. And now let me plot this function. Well, this is the function. This is not the derivative. This is the function. Okay. And you can see where the function has, say, one peak here, another peak over here. I can change the range. I may take a range, say, -10 to +10. And you can see, okay, it is an interesting kind of a function. Probably there is a peak over here, but it may not be. Okay, but there is one peak here, there is one peak here, there is one peak here, and then probably it is going asymptotically to 0 as x goes to plus or minus infinity. Okay, of course, looking at the degree of this particular equation, we can also guess how many solutions it should have. Okay, so well, it seems to have here 3 real solutions. Not solutions, but the extrema and minima, the 3 at 3 different points. Now, what you observe, this is only a potential function graph. I have not yet plotted the derivative part. Okay, this is only potential function. What you observe, the potential is minimum here, maximum here, again minimum here. So this is double well potential, and when you consider the double well potential, okay, the potential is minimum over here, so this is going to be an equilibrium point. This is also going to be an equilibrium point, and both these are stable equilibrium points. Okay, so if the object is at this particular distance, okay, it will have minimum potential. You see at this right hand side well, okay, right hand side bottom, okay. And similarly, if I slightly disturb the particle, okay, it will tend to have greater potential, okay, and then it will try to come back to the lower potential because that is the equilibrium point, and due to inertia it will continue on the opposite side and keep oscillating within this particular potential well. Similarly, the particle can oscillate on the left hand side potential well, okay. And at the center again over here you see the maximum potential. If I'm going to keep particle at this point, it is going to be in equilibrium, but it is unstable equilibrium. You slightly disturb it, it is going to roll down on this side as well as on this side. Okay, I mean depending on where it gets disturbed. So if it is disturbed slightly on right hand side, it will roll down here. If it is disturbed slightly on left hand side, it is going to roll down here. Now see why we can even make this kind of imagination, that I can imagine this as some kind of a surface, and I can keep a small marble and I can disturb this. Because in reality, when you have surfaces like this, the gravitational potential actually behaves with the curvature of the surface. And you disturb the particle, under gravitational force, it is going to get disturbed, it is going to fall. So this can be directly visualized as if this is a surface and you are keeping a marble and you are disturbing it. The analogy works perfectly because in the real surfaces, the gravitational potential is actually behaving like this. Remember, the gravitational potential for a small change in the surface, okay, varies as the height. We say mgh, okay, from the bottom. So gravitational potential energy behaves exactly according to the profile of the surface, and therefore we can have a good imagination of what will happen in such kind of a case. Now let me calculate the derivative of this, and I will have to calculate the negative derivative. Here I have calculated positive derivative. I will have to put negative sign so that I will get the force, because force is negative gradient, negative slope of the potential. So I put that, and I will calculate that till the end. So I just have put extra negative sign over here. Now this is my force field. This I will call potential, V as a function of x, and this I will call F as a function of x. Okay, and I am going to plot this additionally. So I'll select data here, add the next series. I will say this is force. This series name I will call it as force. X values I'm going to take from x1 to xn minus 1, and y values I'm going to take this c6, which is derivative from at x1 to xn minus 1, derivative at xn minus 1.
Just one clarification, please.
Yes.
How did you put the sheet number in that slot?
Which number?
The sheet number. When you added the data, you have to enter the sheet number and then the range. The sheet number, you are doing some click.
No, I'm not adding right now here. When I directly go for select data, okay, see there is a provision. Suppose I add, and if I click here on the right hand side instead of directly typing, okay, then wherever I click here, it will automatically pick up the sheet number. So you see, when I click on this cell, it is automatically picking the sheet number because it is from this sheet. If I had clicked, say suppose I don't want this, I remove this. It was just mentioned here. If I click on this and I want to pick up data from another sheet, so I click on sheet 2 and I click say on this cell, it has automatically taken sheet 2 exclamation mark and $B$3. Okay, so this right hand side small box is actually helping us to pick up from which sheet you want to collect the data. So I can always write my functions in one sheet, and I can insert a chart in another sheet. Okay, I will have to click on this right hand side and pick up the data correctly. So when I click on the cell, automatically it will pick up from which sheet it is taking.
Okay.
Is it fine?
Yeah, thank you very much.
Yeah. So yeah, so now this is for this particular potential function. You see the red curve is the force function. Okay, and what you observe here, wherever those extremas were there in the potential, the minima and the maxima, you see the value of the force is becoming 0 at that point. The force is also varying. Also, what we observe at the center, I mean, this is something very interesting and useful. See at the center, what you are observing here, okay, is I said this is the I mean, this particular point is the unstable equilibrium point. And when you calculate the force, you see what is happening. The force is having a positive slope, and it is almost a straight line around this particular point. What does that mean? That means that the force is proportional to x and with a positive sign. So slightly I disturb on, say, right hand side, positive side of x, the force will also be positive and we will try to push the particle even further. Or if I push the particle slightly on negative side, okay, on force side, on slightly negative side, the force will become negative, which means it will push the particle on negative x direction, and the particle will be pushed further away from this equilibrium point. That's why we call it unstable equilibrium point. Whereas if you look at the zero of the force when the potential is minimum, you see again in the small region it is like a straight line but with a negative slope, and that is the Hooke's law force. Similarly, here on the right hand side bottom of the well, you can see that force is becoming 0, and in a small region it is behaving almost like a straight line. It is Hooke's law force. Okay, so we have got Hooke's law force in this small region, small oscillation region. Okay, and then if I am interested in finding out how much is the slope in this particular region, well, it is possible to do that. Okay, then you can pick up this particular value and one can calculate what is the slope at this point. Okay, and we can expand in this small region and we'll calculate. So tomorrow we shall see these things. Okay, when we are going to talk about the error and how much extra error might come. Okay, so that time we'll discuss how to pick up this particular point and calculate the slope. Okay, so we'll have an assignment on that.
Sir,
I think there are many comments and questions here. So let me just go through them. Okay, so there is a question, Kanan, at end points, can we take the left-hand derivative and right-hand derivative? Yes, it is possible that you may be able to do that, but then you are not finding, remember, the derivative at that particular point with the kind of definition I gave, the next point of and the earlier point. Okay, so you may be able to calculate the derivative at the half interval. So yes, it is possible. For the sake of completion, you want to have complete graph, you may do that. Okay, but those are not generally, endpoint derivatives are not generally very reliable things. That is first thing. Abhijay has asked, okay, that does not make, he's trying to answer that. And I think there is a discussion about that point. Why this method will be helpful in comparison if we find a derivative analytic and plot it as a function. Okay, I mean, yes, in numerical method, you can do the same thing that you are doing in analytical method. And I mean, right now we are dealing with some simple functions, but even when complicated function comes, you see I had made the same template and I am changing the function and things are working. Okay, as long as nicely behaving function, it is working. What if V0 is okay, negative potential? So it is asking. So yeah, we can try out that. So if I have got negative potential, V0 is -1. You get the mirror image, and here you have equilibrium at the center, and then there is a potential hill. Yeah, so that's one of the yeah, there was that's so if V0 is negative, you are going to have something like this, a function something like this, and you see here there is only one stable equilibrium point at the center. Okay, you want to go to more stable point, you will have to cross over this potential hill and then go over. So yes, by changing one variable, see, the beauty part of it is we just change one variable and you automatically start seeing things. Okay, because once you have created a template for this data calculation, okay, things become really easy. So you can just change the function the way you want. Only in case you want to change the resolution, you may have to change x minimum, x maximum, and precisely calculate with that.
Sir.
Coming to next,
Sir.
why is extra negative sign put in column C? Because in the column C, I am not calculating derivative in this case. In column C, I am calculating the force, and force is given as negative gradient of potential, so negative derivative of potential. Therefore, I had put extra negative sign in column C. Yeah, Srisham has written that f is minus dv by dx. Show how you made the template. So, okay. Well, the question of becoming fast is not a big thing. I told you the certain shortcut keys, and well, the experience makes it different. I have used it so many times that I am relatively faster. You have just started doing it for 1 week. So, okay, you start working on it, you will be faster. Don't worry about that part. Okay, some shortcut keys, they are not specific to Excel, they are specific to all Office products, even in Microsoft Word, are this use of Control Shift keys along with the motion arrows keys. So you may jump with Control key, Control down arrow, Control right arrow, Control left arrow, and so on. Similarly, Control home will take you to the very first cell, Control end will take you to the very last cell. Okay, some of these things, and along with that, if you press shift, then up to that point everything is selected. So these are very common shortcut keys, okay, for any Microsoft Office product. Yeah, any question?
So can you please try the double derivative of v of x?
Double derivative. Okay, let me just, this is the first derivative that I'm talking. If I want to calculate the second derivative, I will go to the, I can use a simple rule. I can calculate the derivative of derivative. Okay, so I will calculate here equal to, see in the bracket, this y2 minus order y1 divided by, I have to go back to x. Okay, so again in the bracket, x2 minus x1. Sorry. Okay, and I can do that up to E1003. Okay, and then if you want, I can plot that. Let us select this chart, bring it here, select the data, add new series. I will say second derivative. Actually, it is not second derivative. It is, to be real, it is jerk, because it's a derivative of force. Okay, and x values are going to be from this point to this point, and y values are going to be this point to this point. And yeah, that's it. So what you observe is this green thing is this derivative of force. Okay, and what you observe that wherever the force has a peak value, this will have zero value. Okay, so I mean, many times this may not have physical significance, but well, you wanted, I have plotted. Okay, this is, we'll need this kind of thing, especially when you are discussing, in place of x you are writing time and you are writing velocity and displacement, and then you can calculate acceleration like that. Okay, so yes, this becomes useful if I want to calculate, if I'm given distance versus time graph and I want to calculate the derivative of that, which gives me velocity, and I want to calculate acceleration, then I need this. So from displacement time graph, I can calculate velocity curve and acceleration, or the force as a function of time.
Thank you very much, sir.
Yeah, welcome.
So can you once again show the derivative of x?
Derivative of?
F, the formula.
Okay, the formula was exactly similar. Now, for calculating derivative of f, I'm treating f as y. Okay, and x remains as it is because I'm taking derivative with respect to this x column. So what I'm writing here is, let me click on the formula bar. What you observe is I have picked up the next value of the force and the previous value of the force. Okay, that difference divided by difference in x for the same corresponding values of f. Okay, so when I do this, what I'm getting is the derivative of force. Okay.
Yes, thank you.
Yeah, welcome.
So in the column x, how do you reach to the x max? Like from the formula?
Okay. Yeah, so see, the original template, what I've done is I have written x max, x min, dx is my x max minus x min, and I have decided I want to go for 1000 points. Therefore, I have already defined it for 1000, and then here I'm going from I'm just adding that incremental value of dx, everything, and I want to check the last value. I just press control down arrow and I get the last value. Yeah, that is 10. It has to match because I go on adding the same amount.
Excuse me, sir.
Okay, sir.
Yes.
Excuse me, sir.
Yes.
Can we calculate higher derivatives without calculating the first derivative?
Yes, it is. I mean, it is possible in a way of, see, in numerical method, you will have to calculate. Okay, but you may calculate analytically and you may put that, but that becomes meaningless.
Sir, in this particular case, if we want to calculate the fifth derivative and all, we should calculate till the fourth derivative.
You will have to calculate. Yes, the numerical technique, you have to calculate the differences. Okay, first difference, second difference, third difference, and so on. So yes, you will have to calculate.
Okay, sir.
And in general, when it comes to physics problems, second derivative and third derivative, at the most, sometimes you may need third derivative. Generally, second derivatives are good enough, useful. First derivative and second derivative is what typically we look at. Okay, so we generally don't need higher derivatives in physics. Okay, let me come to now some simplest way of solving certain differential equations. Okay, and then we'll see more and more complicated cases. Okay, so first we'll talk with simplest of the differential equation. Now, for that, in order to understand how differential equation is typically, one solves, let us go back to the presentation. Just a minute. Is this visible? It will come.
Yes.
Okay, so let us take various cases. First order differential equation. First order differential equation, you observe at many of these kind of problems in radioactivity, charging, discharging of capacitor, growth and decay of current, Newton's law of cooling, or variation of atmospheric pressure. Okay, the simple, if you take simple model, so you get first order differential equation or Beer-Lambert's law when you're talking about light passing through a medium and it is getting absorbed, okay, and how much part it gets transmitted. That also becomes useful in astronomy when you're talking about how much starlight will reach through at different altitudes, because as you change the altitude, the effective thickness of the atmosphere changes. So, I mean, these first order differential equation becomes useful in many multiple cases. Okay, so let us start talking about the first case. Let's take this example of radioactivity. We have taken a very simple differential equation, dn by dt equal to minus lambda n. We convert this into difference equation. So in our case, this dn will become actually the delta n. Okay, because it is going to be finite difference. It is not infinitesimal. In analytical calculus, you bother about infinitesimal things. In numerical calculations, you have to talk about finite difference because you are actually taking some values. That finite difference you can make as small as possible depending on how many iterations you are ready to do, how much time you want to spend on that. Okay, because more iterations, naturally it may take more time and also more resources as far as your computational source is concerned. Okay, so here I can write this dn as minus lambda n dt. What is dn? Dn is the next in time interval value minus the earlier time interval value. So at one particular time, say t1, the amount of radioactive atoms was say n1. At time t2, it is say n2. Then dn is going to be d2 n2 minus n1 minus lambda times n1, the original number. Okay, the new number is going to be dependent on the original number, and therefore it is n1 here, into dt. Dt is that time incremental step, or t2 minus t1. Okay, so you can then shift this n1 on the right hand side, and you get n2 is equal to n1 minus lambda n1 dt. This is how you are going to calculate the new value. So n2 value, you are going to, it will be based on n1 value, and n1 value minus this part, out of which you see the lambda I is going to be the constant given in the problem. Rest all you are going to find out, and of course n1, n0 will be given to you. What is the initial number of initial number of nuclides present? Okay, that will decide how n varies as a function of time. Okay, so we can then iterate this loop for small increment in time. Okay, so let us do that, and then we can come to the next problems in that. So let me quickly share the Excel. Is the sheet visible now?
Yes, sir.
Yes.
Yeah. So now what I've done is, okay, let me go back to the required template itself. I will delete this chart. I don't want this equation. I will have to rewrite functions and all of the things. So let me delete all that. And what I need here, in my problem, n0 value is given to me. Okay, how many number of atoms or how many number of these radioactive atoms were present in the beginning, and I'll be giving, in place of x, I'm now talking about time. So this is going to be say some t maximum and t minimum I'm going to talk about. I may start t minimum with 0, and this is going to be dt. Okay, so what I've done is now my x variable is nothing but time variable. I also need value of lambda. Okay, so I keep value of lambda here. Fine. Now let us take any case. Okay, I will take say lambda. Lambda depends on half life. So suppose you are interested in say half life first. Okay, and this time interval t max and t min is could be in any unit. Okay, so let us suppose half life is say 5, and I go up to say 20. Okay, I just decided half life is 5 units. Now that unit could be days, that unit could be seconds, that unit could be minutes, it could be years, it could be 5 million years, it could be anything. But in the same unit, I'm going to talk t max also and dt also. Okay, so when we say dt has to be small, how small is I said the important relative question. So if I'm saying talking about 5 million years as my half life, then I'm talking about one step as 0.02 million years. Okay, which is basically 20,000 years. So my one step is 20,000 years. Now you may say that, I mean, in what way you are saying that this delta t is very small, 20,000 years. As compared to half-life, yes, it is very small. Okay, so let us calculate n here. Now I have to solve this problem. I'm not going to solve it analytically. You know the solution. You know it is exponential solution, but see how we are going to do it. Looking back into that, my first value at t equal to 0, the value is going to be equal to n0. So I'll just say this is equal to n0. Okay. Now what is n0 value? I have not written, but let us suppose I have got initially some 1 million particles. So I have just written 1e6. The half-life, is lambda, is log of 2. So ln 2 divided by half-life. Okay, I got some number, and ln is natural log function. Okay, in Excel. So ln bracket 2, I'm writing divided by g2. G2 is half-life. I don't need to log because these values are going to be fixed. But when I'm going to use these values here in the formula, then I will have to log those cells. Okay. Now let me do the calculation over here. What I said, my n2 value is going to be n1 value minus lambda n1 dt. So this is going to be my previous value, n1 value, minus lambda is f2 here, but I will need to log that $f$2. Okay, into the previous value, therefore n1, again b5 I am writing. You can look at the formula either here or in the formula bar, multiplied by dt, which is my time increment step. So I don't have to calculate from this, t1 minus t0. I can straight away pick it from this point because I'm going to keep that constant. So it is $a$2. Okay, I have written this. Now I have to paste this formula everywhere. I have taken 1000 cells, so I will go up to B1005. Select that, paste it, and well, it came to some value. Let me plot this graph. Let me plot this graph. And you see that nice exponentially falling behavior. Nowhere in this function you have written that exp minus a5 kind of a function over here. Okay, so it has solved the differential equation, and this is what the solution is. You can see at t equal to 5, it has reached the half the value. Okay, between see this about 4 lakh to 6 lakh, halfway it has become correct. Okay. If I want to see that nicely, what I can do is I can take half-life as, or the initial value as not 1 million but 1.2 million. Suppose I do that, initial value as 1.2 million, then you can clearly see at x equal to 5, it is coming exactly half, which is 0.6 million or 6 lakhs. So our solution, I mean, this is again, we have taken a simple problem, but solution works very nice, fine. Of course, you can do later formatting and put the chart title and all other things. Okay, but any question at this point?
So can you please show the formula for n once more?
Yeah. So let me come back to the screen and let me show you the formula first. So this is the formula. N2, that is the next value that you want to calculate, is the earlier value minus lambda earlier value into delta t. And your earlier value is
lambda
the
negative.
Pardon?
We have not kept that minus sign when finding n2 minus n1.
You have taken this C minus lambda n1 dt.
No, sir. In the Excel sheet, the n that you designated.
See, this is my final formula. I'm calculating n2. So n2 is my new cell. Okay. In the new cell, what formula I'm going to put? Don't read this as n2 as equation. Read this as n2 is assigned with this value. So my formula starts from equal to here, and rest of the things are put. N1 minus lambda n1 dt. Yes?
Sir, can you please show that Excel formula that you entered?
Yeah. So I shift back to Excel. And look at the formula here. Yeah. The formula is B5, which is the earlier cell, like N1, minus $f$2, which is lambda, into N1 into delta t.
Okay, sir. Thank you.
Yeah. So this gives, you can clearly see that the variation, okay, is going to depend on what is the difference equation that you're going to write. Okay. Now, what we can do is we can go to a radioactive series thing. Okay. So let me just.
Sir, excuse me.
Yes.
Sir, I typed the same formula as yours and almost and written also in same cells the value, but I am getting different value.
Okay. What is the what formula? Can you read the formula?
Yes, sir. B5 minus $f$2 star B5 star $a$2.
You have written that, and you have copied that formula everywhere, right?
Yes, sir. My first, first value is getting error. It is 9.9 raised to 5.
So what is the lambda value you have taken?
It's the same log 2 divided by 5. That was 0.1386. That's
and what are your T minimum and T maximum values?
0 to 20.
And
what is the first value? It is correct, sir, I think, because he says the 9.9 into 5. So it is 997227. So it is approximately.
So first value, right now I changed my N0. You see, the first value, when I had taken originally, yes, it is correct.
Okay, sir, yes. And not value.
It's just to show you that, at half-life, you get half the value. I just wanted that reference line of, that 0.6 million. Okay, therefore I had changed in the second case, I had changed the N0 value. So if N0 value is 1 million, yes, that is coming correct.
Yes, sir. Thank you, sir.
Yeah, thank you for pointing out okay, this part. Okay, so let me shift back to the presentation, and we go to a slightly more involved problem, because this was probably a relatively simple problem, but it is useful illustrative example, I would still say. But let us go to a radioactive series problem. Okay, what is this problem? You have got a series A disintegrating into B, B disintegrating into C, and then you write formula that A is radioactive with some decay constant lambda A, B is also radioactive with a decay constant lambda B, and C is going to be a stable product. Okay, now if you have solved this particular problem analytically, you need to use one particular trick at some point, that you multiply with the common factor e raised to lambda B t, okay, and then you need to manipulate that and you can solve. Okay, the problem is solvable. It's not a big thing. It's just that two differential equation, or rather three differential equation, you need to solve. Now what we do in this case is a very straightforward thing. You calculate the new value of A, okay, NA as the old value of NA. Now you see, this is not an equation, this is an assignment. So NA is assigned with the old value of NA minus lambda A NA delta T. The new value of B is assigned with old value of B plus lambda A NA dt. Remember, because this is the rate at which B is getting produced. And third term minus lambda B NB dt, this is the rate at which B is disintegrating. But it is disintegrating at a different rate, you see, because this is lambda B and this is lambda A. The rate at which B is getting created is decided by this decay constant of A, and the rate at which B is disintegrating is decided by its own decay constant. At what rate C is getting generated? So C will be generated only when B is going to get disintegrated. So B disintegrates at this rate, and therefore C will get generated at this rate. It is not going to be dependent on the rate of fall of A as far as expression is concerned, but the actual numbers are concerned, it will depend, because the number of B, the NB value, is going to be dependent on NA value and lambda A value. Okay, so ultimately, just by writing these three things, it is possible to simulate this entire problem. Okay, and
Sir,
let us go for that. Yes.
here NC is also decaying, right? So
No,
we
NC
do
is
not
not
have that.
decaying. NC is not decaying. NC is not
Okay.
decaying into D.
Okay. Yes, you said that it is a stable. Okay.
Yeah, C is stable. A is disintegrating. B is disintegrating. C is stable. Okay, you may write, of course, 4, 5, 6, 7 series. You can also, in fact, it is a very useful exercise. You can also write this series for the natural radioactive elements. The problematic part there is there are large number of elements. That is not a problem. Excel can handle that. The half-life can be extremely high or extremely low for certain intermediate elements. Okay, but well, Excel will still do the calculation, and that should not be a problem. Okay, it's just that final graph you will realize that what is going to be the relative proportions of the elements which are going to be present. So let us do this problem. Let me come back to the Excel sheet. Okay, is the sheet visible?
Yes, sir.
Yes, sir.
Yeah. So let me, I mean, NA part remains the same. I will just write this as NA. And I want to calculate NB here and NC here. Okay, and I will have to write the difference equation for them. So what are my initial conditions? When you want to solve a differential equation, first order differential equation, you need one initial condition. Okay. And if it is second order differential equation, you need two initial conditions. That is because whenever generally you are solving a differential equation, you are doing an integration, and integration will need, there will be constant of integration, and if you give initial condition, that constant of integration can be determined. Keeping that in mind, here again there are three differential equations, first order differential equation. So you will need one initial conditions, and those are one actually boundary conditions, but here they become initial conditions because you are putting condition for t equal to 0. So initially, let us suppose B was not present, so I am writing 0 for that. C also was not present, only A element was present, and we want to see how B and C will slowly develop in time. Okay, now we need one more constant here. So this is going to be lambda A. Right now it will write as lambda A. Half-life for A it is. So let me write this as PA. And let me also write half-life for B and calculate half-life for B here. So suppose half-life for A is say 5, half-life for B could be larger or it can be smaller. Let me take a smaller number, something like 2. I think no, I thought the connection got a. Am I audible clearly?
Yes, sir. Yes, sir.
Yeah, thank you. Yeah. So here, let me calculate this. So what I've done is I have calculated lambda for A, lambda for B, and let me write the difference equation. Keeping in mind, the new value of B is going to be the old value of B. See, for integration is always going to be that, okay, the old value. In that, you are going to add that difference. Okay, so plus, I'm writing plus because the rate at which B is getting created. So remember, it was lambda A N A, okay, into delta T. Okay, so it is going to be lambda, that is $F $2 into NA in the earlier cell, okay, minus lambda B, which is $H $2 into
Sir,
NB.
you probably forgot dt
Yes, I have to write dt also.
after B5.
Correct. I have to write. So let me put. Thank you for ensuring that. But I will have to put this in a bracket. Okay. So this is lambda B NB dt minus lambda A NA dt. So I can multiply here with dt. So $A $2. Okay, or individually I can write that $F $2 into B5 into dt minus $H $2, which is nothing but lambda B NB dt. See, what I'm doing is whenever I'm calculating B, I'm using values of the earlier iteration for NA as well as NB. Though I have calculated NA at this time interval, I'm going to use values from the earlier reference only, earlier interval only for lambda A as well as lambda B. Okay, so that point you have to keep in mind. And now I will write equation for C also. So this is equal to the old value of C, and it is only going to get generated. So it's plus lambda B NB, which is $H $2 into NB value. Okay, and it is not, and multiplied by dt, so $A $2. Okay, and it is not disintegrating, so there is no term to subtract. So I calculated both these. Now I'll copy paste both these from C6 to D1005. Okay, so I copy pasted this. Now let me plot all three things. So I have selected all three things. Again, the same shortcut keys, Control Shift down arrow, right arrow. Okay, or Control Shift End, so that I can go up to the last point which we have changed, modified in the Excel sheet. So that is one interesting part of Excel, that it recognizes when you say end, it has to go to not the last cell of the Excel sheet, but wherever you have entered data. Okay, so that is one good part about Excel. And then I will plot this, and yes, you get three series. So you see what is happening. The blue one is the series 1, it disintegrates. The red one is the intermediate value, the daughter nucleus, it increases and then again it comes down. And the green one is the third series which goes on increasing. Okay, now depending on the half-lives of A and B, things can change. For example, see, I have done the iterations up to 20 units. Okay, but half-life of A, half-life of A is say 10. Okay, and half-life of B is say 8. So you can see that the values are going to change like this. Half-life of A is say 5, and half-life of B is say 8. Now what is happening? B is relatively more stable, so its absolute number is going to increase. Okay, earlier it was less stable. Okay, its half-life was smaller, so say I had taken 2, and therefore the total effective amount of B is not going to increase by large amount, because it is getting created at a certain rate, but it is disintegrating at faster rate, and therefore it will reach some peak value, but then ultimately it is not going to go to really high value. That will be possible only if the B has half-life of larger value, something more than say 5. Suppose B has half-life of 10. Okay, then you see that B significantly starts getting accumulated. Okay, so these plots are useful also when you are learning new things in physics, that quickly you can simulate and you understand the physical interpretation rather than only getting lost into the equations. Of course, reading equation and physically interpreting that from the analytical equation is also an important skill. Okay, but graphical methods many times can assist that. So this is one example I wanted to emphasize. And then we'll go
Sir,
to yes.
Could you take TBS 5?
TBS 5. Okay, both equal. Yes, this is possible.
Sir, can we get a point here that all three population is same, like
Yeah,
NA and B? From this graph, it seems like we can have by adjusting PPO.
Yes, it is possible. If I take 4.6, no, 4.3, 4.3, it is possible. Out of interest, you can say yes, there is a one particular point where if these are the ratios, all three populations will be same. Let me tell you one point.
Could it be useful or something like that? I am guessing.
Okay,
like
so I'm coming to that. I'm coming to that. When it comes to radioactive atoms, the number of atoms are not useful in as such, or they are not even directly measurable. What you measure is the activity. Okay, and what is activity? Activity is the rate at which the object is, the particular element is getting disintegrated, multiplied by number of atoms existing. Okay, so lambda into n, that is the activity, that is the rate at which it is getting disintegrated. So you have detectors which will detect the rate at which things are getting disintegrated. And what becomes useful thing is when the activities of both Na and Nb are same. Those kind of cases become useful. So, well, yes, instead of plotting n, I can also plot activity. So what I can do is, let me calculate activity of A and activity of B. I don't have to do much. I just have to multiply this with lambda. Okay, so $f $2 multiplied with NA, and in fact here it would have been useful if it is not immediately the next cell. Okay, and here I say $h $2 multiplied by NB. Okay, and now both these, let me apply the formula and let me plot the activities. Okay, so I'm going to select this and I will select this range. Okay, so I have selected this range, I have selected this range and this range. Okay, now let me plot this. So you see the activity of the two after long time is going parallel, which means they are in a particular ratio. Now let me take, because I have taken calculation up to 20 units, let me take these numbers as smaller numbers. Let us suppose half-life of A is 2 and half-life of B is, say, maybe 1.5. Okay, or now here what is going to happen? If I calculate sufficiently long distance, the actual entire number is going down. But if I take sufficiently long distance over here and I do the calculation, then I realize that both these are not actually going to zero. They are becoming very small. Say for example, if I go over here, they are becoming very small, and the two numbers are in a particular ratio. Okay, this is like something like 350. This is 1250. Okay, this is again around 350. This is 1250, and so on. Okay, let us take a case where A is really long living and B is very short living. Okay, and then you talk about what you call the secular equilibrium. So here you see what is happening is both are quite close to each other. Let me take B has one half-life. So both effectively become very close to each other. Okay, and what does that say? That says that when the difference is very large, I take equal 0.5, both activities are almost same. So see, this is this has got a physical significance, that A is slowly decaying, B is fast decaying, but what you observe is their activities are exactly same. But that also means activity is, you see the lambda B value is very large as compared to lambda A value. So if activity are same and lambda or decay constant of one of the element is very, very large, it would mean that that particular element will be equally in small proportion. So here the ratio is 20, and then you will see that in the detector you will detect both equal activity, both A and B element giving equal activity. But what it really means is in the chemical composition, B amount of B will be something like 1/20th of amount of A. This becomes useful in geology. Okay, in geology, when you are looking at disintegration, and if you know the half-life, you can calculate what is lambda value, and that can tell you what is the chemical proportion of particular elements in the given rock.
Yes,
Yeah. Thank you. So let us come to, this is almost just 1 minute left. Yes.
Can you show me C formula for C, NC once, because I'm encountering some problem.
NEC is
NC.
Yeah, NC. Okay, NC is the earlier value of C, D5, plus disintegration of D5, B.
Okay, disintegration of, okay, C5, okay, yeah.
C5, you see,
and
C5, $A, $2 is delta T, and $H, $2 is the decay constant of B.
Okay, and what
so
about?
It is lambda B NB dt.
Okay, lambda B NB dt.
Yes.
Thank you, sir.
Because B is disintegrating, so C is getting created.
And sir, significance of activity you just showed.
Yes.
So how exactly that activity is going to say if we increase the amount, say substantially increase the amount, then
when the entire graph will be scaled up. That's it. So if I take, instead of 1 million, if I take 1E10, okay, the graph has scaled up. The nature of the graph will remain same. So everything will be now 10,000 times greater. So activity also will be 10,000 times greater.
So
because the amount of number has increased by 10,000 times. Yes.
So we can increase the number of elements now, like it is ABC. So
Yes,
we can
yes,
take
yes.
up
Instead
to
of
which we
ABC,
get
you
a
can have A, B, C,
stable.
D, E, F. You can have 8 elements, 9 elements. The logic is exactly going to be same. The last table element, whether you want to plot or not, is immaterial. Even if I don't plot NC, it doesn't make a difference. I'm interested in only disintegrating elements. So I just deleted NC right now. See, but I'm not using that anyway in my graph. Only when I wanted to show that how A is changing, B is changing, and C is accumulating. Okay, that graph NC was important, but when I want to study their activities, it is not important. I just deleted it. I am not using it anywhere. Okay, physically, what does it mean? Once the uranium has disintegrated, say, into radium, what radium is going to do, uranium is not bothered. You remove, say, lead from the rock, the other elements are still going to disintegrate the way they are. So I have removed C column here, but my activities are not going to get affected. I remove A column, then it will get affected. I have added now, when Rohit asked, I have added 10,000 times more material. Okay, so everything scaled up. Yes.
So where we can also find the value of time at which B is becoming maximum, like before B starts disintegrating,
See
it
here,
reaches maximum.
At NB, this is activity. The activity of B is becoming maximum at some particular point. So yes, in the Excel, when you have done the calculation, you want to find out at what time it is becoming maximum. You can do that, and that is where you can find out you can use the max function, okay, and you can use that. Say for example, let me calculate equal to max of this value, okay, and I can also now find out, okay, what is going to be the index for that. Okay, you learn the index function, and you learn the okay, so you can give array of T and you can give array of this. Okay, let me just quickly check that index. Okay. So I'm looking at sorry, if I want match. Okay, so I can use this match function. I want to look up for this value, and I want to check the array from here, this, and I see at 1001 I'm getting this. Okay, so I got the index at 1001, I'm getting this maximum, and I expect that at 1001 I should be getting maximum, because my incremental step is 0.02. So 1000 into 0.02 gives me how much? About 20 or so. So it gives me that. Okay, so you can use wait. Let me write here F5 to F1005. No, I didn't get the match for this. and I want smallest number.
C5.
No, this was the maximum that you got. Wait, what are we plotting? We are plotting activity of A and activity of B, right? Yeah, just a minute.
H2C5, C5 plus H2C5 into,
And I take let me use this index function. No, I don't have to use index. I have to do the matching only, but it has to go on decreasing, right? So let us find out where this is maximum. Let me reduce this. To C5. Yeah, this is correct. Let me just quickly find out. Format cell, and you go to scientific number because that helps me comparing things. Yeah, so this has shown correctly. Whether it is match for this value in this array and 1, or I will put exact match. Yes, see, it gave me at 114 I am getting at 114 step I am getting this. Okay, so 114 multiplied by 0.02 will give you how much? Into 0.02 multiplied by this. So 2.28, and that is what we expect here. So at around 2.28, there is maximum over here. Okay, so 2.28. Okay, this is giving you where exactly the peak is. So you can use other functions of Excel also here to find out where the peak is. Yeah.
Yes.
Yeah. So thank you for that question. So we explored something extra. Okay. Yes. So what we'll do is we'll stop today at this point, and tomorrow we shall discuss the cases of harmonic oscillator and the second order differential equation, those cases. Okay. This method that we used is called Euler's method. Okay. So some theoretical aspect of that also we'll discuss in tomorrow's session. Fine. And wait for more assignments on this. So thank you.
Just one more thing, please.
Yeah, please.
In that match function, you found out 114. That means the 114th row is matching with the peak.
Correct.
So if I want to find out the time, or what was the activity of A, or what was the amount of A, everything I can find out.
Yes, it is possible to find out. In fact, VLOOKUP function helps for that. Right now, I'm not exactly aware of the exact syntax, but we can explore that. And tomorrow, I will incorporate that in the tomorrow's problems. Okay.
Thank you. Thank you.
Yeah. Thank you.
So, can you show the formula of activity once more?
Yeah, sure. Let me go back to that. Activity is just lambda into the number. Okay. So here, for example, I want to find out activity of this A. So it is $F$2, which is nothing but lambda A multiplied by B6. B6 contains the number of atoms of A. number of nucleus of A.
Okay, sir.
Okay. Similarly, for activity of B, it is lambda B multiplied by number of B, NB. Okay, so we shall continue tomorrow with